Hi everybody, this is a little mini lecture that's going to take you through how to interpret GCMS data. So when you ran the distillation, you handed in sample vials that were then run through our GCMS instrument. GC stands for gas chromatography and MS stands for mass spectrometry. Really, this is two separate instruments that have been linked together. So what that really means and what we're really looking at here is for the gas chromatogram part, gas chromatography really encompasses all of this part. And then what happens is the sample travels straight from the GC detector on into the mass spec instrument. So our samples get injected at the injector port and go through a column. Once they're injected, they're actually heated up a lot to the point where they vaporize. They become a gas. They go from a liquid state to a gas. And the carrier gas is going to push those molecules then through this column. The molecules are going to travel through this column at different rates and be recorded when they come out from the GC. Once they go into the mass spec instrument, this is a whole different ballgame. It's actually going to take these molecules and bombard them and break them apart. The best analogy we have for what a mass spec does is pretend you have a piano and you're gonna drop it from a 10-story building. Once you drop it, the piano breaks into a whole bunch of pieces that if you can find all the pieces, you could put it back together again and still get a piano. So the GC itself, what the GC is actually going to tell us in terms of data that it gives us, is it's going to tell us how many molecules there are in our sample. It is also going to tell us the relative amount of each molecule in the sample. We'll look at printouts of GC data in a couple slides here. The mass spec is actually going to help us figure out what those molecules are. It's actually going to help us identify what molecules we had in our original sample that was all the way over here. So that sample that you handed in. When you get the GC mass spec printout, you actually get a 3-page printout, and this is page 1. Page 1 is just a table of the GC data. So what I can glean from this GC data is that I had 2 different peaks, because it actually gives me a peak number, but it also tells me that I had different, what's referred to as RT. RT stands for retention time. That is the measure of time it took that molecule to travel through that column in the GC. Usually, in most cases, your number of peaks is going to indicate the number of molecules in your sample. This is going to assume that everything has a unique retention time. Yes, some things could end up in the same peak. Yes, we could have some things end up in 2 slightly different but close peaks. So really, the things we pay attention to here from the GC results are really this retention time and also this percent of total. This is actually telling me how much of each molecule I have in my sample. So if I look at this, I've got 49.247% of whatever this molecule is that has a retention time of 2.411 minutes. And then my second molecule in my sample has a retention time of 4.220 minutes, and that makes up almost 51%. So it makes up 50.753% of my sample. So if my initial sample was a 50-50 mix of cyclohexane and toluene, whatever I did here to try to purify, it really didn't purify it very much. It's still pretty much 50-50. Page 2 of your printout is actually the picture. This is actually what's considered to be the chromatogram. This is the picture that went with the table on the first page. So on the first page we had slightly different retention time, so this might be from a different run, but again, we had 2 peaks. One had a retention time of about 2.4 minutes, and the other one had a retention time of about 4.2 minutes. Down here at the bottom, the time here is in minutes, and then the abundance here on the side, these 2 peaks look pretty similar. So again, we get 2 pieces of information. We get retention time, number of peaks generally indicates the number of molecules in the sample, and the relative abundance is really, when the computer gives us that number, it's really calculating for us the area under the peaks to give us a percent area. Okay, so if we look at these 2 peaks, they look like they have pretty similar areas. I actually notice a really small peak down here. That one was probably is a real peak and another molecule, but it was below the detection limit that we set for the instrument. Third page of the printout is the mass spec results. So this is the actual mass spec data, but it's interpreted, to be honest with you. So what does that mean? So what that's telling me is your sample mass spec was compared to a library of known MS data. So by doing the comparison, it's able to tell me, okay, you had 2 peaks. You had a retention time at 2.4 minutes. You had a retention time at 4.2. The molecule that came out that is predominantly present in that, the molecule that's present in that retention time peak is cyclohexane. At 4.2 minutes, the molecule that's predominantly present is toluene. So this is actually sort of my page 3 here, really is sort of my one-stop shop, if you will. Okay? Why? Because these 2 things are actually telling me data from the GC directly. This percent area and retention time are the same as what I had on pages 1 and 2. Now it's just been interpreted. Now I've actually got molecule identities. GC doesn't give me molecule identities, but mass spec does. One more thing to watch out for is, okay, so this computer compared the data, how good was the match? And that's where you get the qual number here. This qual number is really telling you how good that match was. So the computer was like 91% sure that this mass spec from your data matched the mass spec for known cyclohexane. You do get a few different numbers here, and it's slightly different runs, slightly different ways in which the mass spec data might have been generated. So getting a match of over 90, think of it this way: if you get over 90% on any exam, you're pretty happy. If you get over an 80%, you're reasonably happy. If you get below that, it depends how happy you are. Okay, so again, my bottom line, my total conclusion here indicates that I have 2 molecules in my sample. I have 49.25% cyclohexane and 50.75% toluene. So I can tell exactly how much I've got and exactly what the molecules are. So what if I get something like this? I'm expecting 2 molecules, right? I'm expecting cyclohexane and I'm expecting toluene. it looks like I have two cyclohexane peaks. They're close to each other. The retention times are not that far apart in comparison to what I got for toluene here. So in this case, what I would do, my total amount of cyclohexane would actually be the sum of 23.42 and 28.18. So my conclusion from this would be that my sample does have two molecules in it because two of the peaks were the same. Specifically, I have 51.6% cyclohexane and 48.4% toluene. Again, what if I'm expecting two molecules and I get something else, right? Well, I'm expecting cyclohexane, I'm expecting toluene, I've got those two, but then I get some other stuff. Peaks 3 and 4 here really are contamination. Where did we pick up the contamination? We have no way of knowing that. It could have been contamination from the column itself. This does tend to happen as the column gets older. It could be contamination from our glassware. It could be contamination from a pipette we used. We just don't know. So one sort of caveat warning is GC mass spec. It's a really powerful technique. It's good at picking up everything in there, including maybe some things that we didn't know or didn't think were in there. Every once in a while, a student will get a contaminant in there, and I'll ask them if they were wearing the gloves, and the answer was no, and it's part of like a moisturizer that they used on their hands. So again, it's really good at picking it up. So here, my results indicate that I actually have 4 different molecules. Specifically, I have 12.31% cyclohexane, I have 87.58% toluene, and I have a total of 0.1% benzene impurities. So I would just call these two, they're 2 different molecules, but I would call them just benzene impurities. Okay? In case you were wondering what the mass spec actually looks like, this is actually a picture of mass spec data, uninterpreted. So the computer takes this, compares it to libraries that also look like this, and then comes up for us with, okay, this is what it matches in terms of molecular structure. And they do that by interpreting the breaking of the pieces. So what we're saying is every time you drop a piano that's the exact same brand of piano from the exact same height, you would expect to get similar pieces every time. All right, that concludes this little mini lecture on how to interpret GC mass spec data.